A warm welcome to science to sleep by setting the tone, explaining that tonight's journey takes us deep into the cosmic mystery of a new interstellar object, 3I or Atlas. The narrator soothes listeners while revealing that this discovery may rewrite everything we thought we knew about our universe. There are nights when the universe seems to whisper. Its voice travels not through sound, but through light, streaming softly across time, reaching the lenses of telescopes that stand like sentinels beneath the cold breath of the cosmos. On one such night, scientists at the Atlas Observatory in Hawaii noticed something unusual, something that didn't belong to the quiet rhythm of familiar stars and planets. It was a flicker, a glint of motion moving against the grain of the sky. At first, it looked like another small asteroid, another icy wanderer born in the outer shadows of our solar system. But as calculations deepened, the numbers began to tell a different story, a story that sent ripples through the scientific world. This object was moving too fast, at a velocity that could not be explained by our sun's gravity alone. Its orbit was hyperbolic, a rare and unmistakable signature. It was not bound to our solar system. It was merely passing through, and with that revelation, a new name was given to it. 3I Atlas, the third interstellar object ever discovered by humankind, the Atlas system, short for Asteroid Terrestrial Impact Last Alert System, had been designed to protect Earth, a network of telescopes scanning the heavens for objects that might pose a threat to our planet. Yet, instead of finding danger, Atlas had found mystery. The observatory's instruments, tuned for precision, traced the faint motion of this newcomer across multiple nights. Data poured in, pixel by pixel, photon by photon, until a clear trajectory emerged. What astronomers saw didn't match the graceful ellipses of planets or the slow parabolas of comets. This object had come from the depths between the stars, carrying with it the history of another world. When the first press release went out, scientists and space enthusiasts across the globe paused in awe. A third interstellar visitor, the headlines read. One Oumuamua had stunned us in 2017 with its cigar-like shape and inexplicable acceleration. 2I Borisov, discovered in 2019, had shown us what an interstellar comet might look like, a more traditional traveler with an icy coma and glowing tail. But 3I Atlas was different. It seemed ordinary at first glance, and yet there was something about it that made even seasoned astronomers hesitate. It wasn't just its speed or its path. It was the subtle oddity of its reflection, the way light danced off its surface, the way its brightness fluctuated as though it were rotating unevenly, revealing surfaces that didn't behave like natural rock or ice. The discovery ignited excitement across observatories worldwide. Telescopes from Chile to Arizona turned their gaze toward this fleeting visitor, hoping to catch it before it slipped away into the void again. Its trajectory cut across the night sky like a fleeting whisper, a narrow window of time, perhaps only weeks, before it would fade beyond detection. Data collection became a race against cosmic time. Every observation mattered, every photon a clue to its origin. The question burned quietly beneath the scientific calm. Where had it come from, and what did it carry? As the object's path was refined, astronomers traced it backward through space. Its direction pointed not toward the plane of the Milky Way, but slightly above it, a strange inclination that suggested it hadn't been perturbed by the gravitational dance of stars or planetary systems nearby. It seemed to have come from interstellar solitude, perhaps the outskirts of a long-dead star system, or from a region of interstellar space where dust and gas wander freely, remnants of creation itself. The possibilities felt infinite. In astronomy, distance and time are siblings. To see something from beyond our solar system is to look into the past. 3I Atlas could have been traveling for millions, even billions of years. Imagine that, an object ejected from its home system, set adrift by gravitational tides, wandering across the endless dark for epochs uncounted, untouched and unseen, until, by sheer coincidence, it crossed paths with our tiny blue world. That alone is humbling. The odds of such a meeting are beyond comprehension. Yet here it was, visible to our telescopes, a silent messenger from another star, For astronomers, interstellar objects are like cosmic letters, fragments of stories written by other suns. Each one carries within it the chemical and physical fingerprints of the environment it came from. By studying their composition, scientists can learn what kinds of materials exist beyond our solar system, how planets and stars form elsewhere, and whether the processes that shaped our own world are universal or unique. 3i Atlas, therefore, was not just another object to catalog. It was a chance to peek into another corner of the galaxy, to see what cosmic conditions might have birthed it. But 3i Atlas wasn't easy to study. Its faintness, speed, and limited visibility made every observation precious. Unlike nearby asteroids that could be revisited for years, interstellar travelers move quickly and vanish forever. This fleeting nature gives each discovery a kind of melancholy beauty, a reminder that the universe offers its wonders only briefly, asking us to look carefully before they disappear into eternity. Scientists knew this would be their only chance to observe it, and so they watched with meticulous devotion, capturing every spectrum, every flicker, every change in light. Even as data gathered, subtle irregularities began to emerge. Its brightness didn't match its predicted model. It wasn't reflecting sunlight the way a comet should. There was no visible coma, no trailing dust tail, no outgassing that could explain slight deviations in its trajectory. And yet, its motion wasn't perfectly ballistic either. Something was influencing it, ever so slightly, as if an invisible hand was at work. Some astronomers dismiss these discrepancies as observational errors or instrumental noise. But others couldn't shake the feeling that this object, like Oumuamua before it, was hinting at something stranger. Public fascination grew rapidly. In online forums and late-night discussions, people wondered if 3i Atlas could be a probe, a fragment of an ancient civilization's technology, or a relic of some unknown cosmic phenomenon. While mainstream scientists remained cautious, the air buzzed with curiosity. For the general public, it was not merely a discovery. It was a story, a reminder that the universe is alive with motion and mystery. The name Atlas itself became poetic. It wasn't just the observatory's acronym anymore. It invoked the mythic Titan who carried the heavens upon his shoulders, watching the stars drift by. In that sense, 3i Atlas symbolized the weight of cosmic knowledge, a burden, and a blessing for those who seek to understand the unknown. As the object moved further from Earth, fading from visibility, astronomers began compiling their data into reports. The more they studied, the less ordinary it appeared. Tiny fluctuations in brightness patterns suggested irregular geometry, perhaps a highly elongated or flattened shape. Some speculated it could be a fragment of a larger body, shattered long ago by gravitational stress. Others believed it was composed of exotic material, possibly nitrogen ice, metallic compounds, or something we had never encountered before. The mystery only deepened when spectroscopic readings didn't align with known cometary or asteroid compositions. Certain wavelengths showed anomalous absorption features, faint but persistent, suggesting a surface chemistry that was neither purely rocky or icy. For some, this meant 3i Atlas might have originated from a region of space very different from ours. A system rich in heavy elements or with a chemical makeup influenced by a different kind of star. The scientific community moved cautiously, aware that speculation without evidence could mislead. Yet behind that professional restraint, wonder glimmered. There was a feeling quiet but powerful that perhaps, just perhaps, this object held clues that could expand our understanding of cosmic formation itself. The very idea that something so small could travel such an immense distance to reach us felt almost poetic. A gesture from the universe, reminding us that we are not isolated, but connected through the shared material of creation. In the United States, where the majority of the public follows space exploration with a sense of national pride and fascination, the discovery resonated deeply. News outlets, podcasts, and late-night science shows shared the story of 3i Atlas, often blending awe with scientific curiosity. For many Americans, it evoked the spirit of discovery that once fueled the space race and continues to inspire new generations. The idea that something from another star had crossed into our neighborhood and that we had the technology to detect it reignited the imagination of a people who have always looked upward and wondered. The night skies above Hawaii continued their silent watch as the data from 3I Atlas streamed in one last time. Each pixel of light told a fragment of its journey, a tale written in motion and reflection. No one could say yet what this object truly was. But one thing was certain. It had come from beyond, and in doing so had changed the rhythm of our cosmic story forever. It had reminded us that space is not empty, that the stars send travelers across the void, and that sometimes, if we are watching carefully enough, the universe will send a stranger our way, just to remind us how much we still have to learn. When the discovery of 3I Atlas was first announced, many astronomers experienced a sense of déjà vu. It was as if the universe had pressed rewind, replaying a moment from 2017, when humanity's first interstellar visitor had swept through the inner solar system and left scientists in stunned wonder. That object, of course, was one Oumuamua, name now etched into the collective memory of astronomy. Oumuamua, meaning scout or messenger in Hawaiian, had challenged nearly every assumption astronomers held about small celestial bodies. It came from the void beyond our sun's reach, moved with a peculiar grace, and then slipped away before anyone could fully comprehend what it truly was. The echoes of that first encounter still resonated when 3I Atlas appeared in the telescopes of Hawaii, as though the cosmos had decided to send a second message, a reminder that its mysteries were far from exhausted. Oumuamua's story set the stage for how humanity would perceive all future interstellar visitors. Its shape, inferred from its fluctuating brightness, appeared elongated, like a cosmic shard 10 times longer than it was wide. Its speed was immense, and yet, it displayed a small but undeniable acceleration that could not be explained by gravitational pull alone. There was no visible tail, no coma, no signs of gas release typical of comets. And still, it sped up, as though something unseen was pushing it. For months, astronomers debated every possible explanation. Was it a fragment of nitrogen ice? A dust-covered rock? A metallic object from an alien system? Or something more artificial, perhaps a probe? A relic? A drifting piece of technology from elsewhere? The data were inconclusive, but the questions it raised reshaped how we look at the night sky. By the time 3I Atlas arrived, astronomers were prepared, or so they thought. Lessons learned from Oumuamua and its successor, 2I Borisov, had refined observation strategies and improved global coordination among telescopes. With each discovery, the community had grown more responsive, faster to track, quicker to analyze. When Atlas detected a new interstellar object, observatories across the planet sprang into action almost instantly. They remembered how little time they'd had with Oumuamua just a few weeks before it faded beyond the range of our instruments, and no one wanted to miss another chance to collect data that could illuminate the secrets of interstellar space. Comparing 3I Atlas to its predecessors revealed striking contrasts. Where Borisov had been clearly comet-like, trailing gas and dust as it neared the sun, Atlas seemed more reserved, more cryptic. It shared with Oumuamua a kind of quiet anomaly, the absence of features that would make it fit neatly into known categories. But scientists had evolved since 2017. They no longer dismissed such oddities as mere observational quirks. They approached them as clues, pieces of a larger puzzle the cosmos was inviting us to solve. Oumuamua's legacy had changed the scientific culture. It taught humility, showing that even in a field as advanced as astronomy, surprises lurked behind every photon. It also taught the necessity of open-mindedness, the idea that phenomena should be investigated without premature judgment. When Avi Loeb, a Harvard astronomer, suggested that Oumuamua might be artificial, a piece of extraterrestrial technology, the idea was met with skepticism, even ridicule, from parts of the community. Yet over time, many admitted that, though unlikely, the possibility couldn't be ruled out with the limited data available. That experience encouraged scientists to approach 3I Atlas with both caution and curiosity. Balancing skepticism with imagination, when early analyses of 3I Atlas began to surface, They carried echoes of those earlier debates. Observers noted irregularities in its light curve, the way its brightness rose and fell in a pattern that suggested an elongated shape or a tumbling rotation. It was faint, harder to measure than even Oumuamua, yet its motion hinted at subtle non-gravitational effects. This immediately recalled the strange acceleration that had defined Oumuamua's mystery. The similarities were impossible to ignore. Once again, an interstellar object was defying the expectations set by standard celestial mechanics. For astronomers, this repetition was both exhilarating and frustrating. Exhilarating, because it hinted at the existence of a new class of interstellar objects that might be common throughout the galaxy. Frustrating, because the fleeting nature of these visitors meant that their secrets always seemed to slip through our grasp just as we reached for them. Each one appeared for only a brief chapter in our cosmic diary, leaving behind data fragments that would be debated for decades. Yet even fragments have power. They force us to revisit our theories, to test the boundaries of what we know. In the quiet hours of the night, while telescopes continued their watch, researchers often found themselves reflecting on the journey from Oumuamua to 3I Atlas as part of a larger story, one about humanity's growing awareness of the galaxy's interconnectedness. Each interstellar visitor is a traveler from another star system, a wanderer ejected long ago by the gravitational forces of its home sun, cast into the endless dark. These objects drift between stars for unimaginable spans of time, untouched by light, until chance aligns them with the orbit of another world. The fact that 3 such objects have already been detected within a decade suggests that the galaxy might be full of them, invisible most of the time, but occasionally crossing paths with civilizations that are looking up. For many scientists in the United States, these discoveries have carried a particular resonance. The country's deep investment in space exploration through NASA, the SETI Institute, and countless university observatories has fostered a public imagination attuned to the possibilities of the unknown. The arrival of each interstellar visitor is not merely an astronomical event. It becomes a cultural one. It inspires art, writing, and conversation about humanity's place in the universe. When 3I Atlas was announced, American audiences immediately recalled the wonder they had felt during the Oumuamua debates. That strange mixture of disbelief and curiosity that had captivated headlines worldwide. It was as though the cosmos had written a sequel to one of the most mysterious stories of our time. The scientific response to 3I Atlas, however, was more disciplined than before. Researchers knew what instruments to use, what wavelengths to prioritize, and how to collaborate internationally for rapid analysis. Lessons from Oumuamua had inspired changes to telescope scheduling and data sharing protocols, allowing teams from different continents to synchronize observations with unprecedented precision. This cooperation revealed another lesson from the first interstellar visitor, that cosmic mysteries require unity, not competition. The universe is vast enough for all eyes to share the same sky. But perhaps the most profound lesson carried forward from Oumuamua was philosophical. It reminded humanity that we are not the center of creation, that even the smallest fragment of rock drifting from another star can humble us with its existence. It forced scientists to accept uncertainty as a form of truth. That sometimes the most honest answer is, we don't know. This humility became the foundation for studying 3I Atlas, allowing researchers to observe without the pressure of instant explanation. It was no longer about proving or disproving alien theories. It was about listening to what the data had to say, however faint its voice might be. In this sense, 3I Atlas was more than an astronomical discovery. It was part of an ongoing dialogue between humanity and the cosmos, a conversation that began when we first looked up and wondered if we were alone. Oumuamua had been the opening line of that dialogue, cryptic and fleeting. 3I Atlas was the follow-up, a second message that deepened the mystery rather than solved it. Each object seemed to say, in its own silent way, that the universe is filled with wanderers, and we have only just begun to notice them. Some scientists speculated that if these interstellar objects were more common than previously thought, then the solar system itself might be constantly brushed by visitors from other stars. They could be carrying with them chemical signatures, isotopes, or even organic molecules forged under different suns. In studying them, we might one day trace the broader story of how matter circulates across the galaxy, how the ingredients for life travel from one system to another, perhaps even seeding worlds with the potential for biology. This idea of panspermia, once speculative, gained quiet momentum as interstellar discoveries accumulated. The legacy of Oumuamua was therefore not confined to the pages of scientific journals. It lingered in every conversation about Three-Eye Atlas, shaping the way astronomers approached the unknown. It reminded them to question their assumptions, to build better instruments, to observe with both precision and patience. Above all, it reminded them that discovery is not always about answers. Sometimes it is about acknowledging the vastness of what we have yet to learn. And so, as Three-Eye Atlas traced its faint path across the night sky, every flash of light on the telescope sensor carried within it the echo of that first wanderer, a whisper from the depths of space, saying that the story which began with Oumuamua was far from over. There are moments in science when data, pure and indifferent, reveals something so unexpected that it leaves even the most rational minds breathless. The night the observation of Three-Eye Atlas shifted from routine to extraordinary began like any other. The skies above Mauna Loa were calm, the telescopes of the Atlas survey sweeping through their programmed arcs, scanning for the faint flickers of motion that betray hidden objects drifting against the canvas of stars. But as the readings began to compile, something strange began to emerge. The data did not line up with the models. The object's brightness varied in a way that was not consistent with its supposed shape or trajectory. Its motion appeared subtly inconsistent with pure gravitational prediction. For those monitoring the live feed, it was as if the cosmos had paused for a moment, whispering that something was not as it seemed. At first, the differences were small, slight deviations, mere anomalies within the margin of error. Scientists are used to noise. The universe rarely offers perfection in its signals. Yet as more observations poured in from independent observatories across the world, the pattern began to solidify. The deviations were real. Three-Eye Atlas was not behaving according to the script written by classical celestial mechanics. Its velocity curve, plotted over time, showed a residual acceleration, a subtle increase that could not be explained by gravitational attraction alone. This was not supposed to happen. Objects moving under the influence of the sun's gravity follow predictable paths, curved gently by the same laws that govern planets, comets, and asteroids. Yet here was something that seemed to drift slightly off course, as if responding to a force that no one could see. In the control rooms and research centers, discussions turned into long hours of recalibration, reanalysis, and recalculation. Teams verified their instruments, cross-checked their software, ruled out errors in atmospheric correction. The data, however, remained firm. The anomaly was not in the measurement, it was in the object itself. The same realization that had once confounded scientists with Oumuamua was unfolding again, only this time with even greater precision. Three-Eye Atlas was small, faint, and yet distinctly non-compliant with the expectations of natural behavior. Its motion defied the cosmic logic that had held true for centuries. As the anomaly became undeniable, telescopes across the globe pivoted toward the intruder. Observatories from the United States to Chile, from Spain to South Africa, joined in the observation campaign. The European Southern Observatory released early data confirming an unexpected spectral feature. Light scattered from Three-Eye Atlas showed irregular absorption bands. The wavelengths did not match typical signatures of carbonaceous or silicate materials, nor did they resemble the icy compositions known from comets. It reflected sunlight in a peculiar way, with fluctuations suggesting a surface that was neither purely reflective nor purely absorptive. Something about its texture, perhaps metallic or crystalline, produced light behavior unseen in any known natural body of its size. At the University of Hawaii, researchers began constructing 3D models based on the changing light curve. The models suggested that Three-Eye Atlas was highly irregular in shape, perhaps elongated, perhaps flattened like a disk, or even hollow in parts. Its rotation pattern was chaotic, inconsistent with the gentle tumbling typical of asteroids. Instead, it seemed to wobble, as though mass within the object were unevenly distributed, or as though its structure were fragmented. The brightness changes were abrupt, not smooth, hinting that its surface might contain sharp angles or distinct faces rather than natural curves. To some, this was the first quiet hint that 3I Atlas was not a simple relic of natural formation. Spectroscopic analysis deepened the mystery further. When scientists examined its light at higher resolutions, they detected faint emissions consistent with volatile materials, but only intermittently. It was as though certain parts of the surface briefly outgassed under sunlight, then immediately ceased, too abruptly to fit the thermal models of a natural comet. If 3I Atlas were releasing gases, the rate was inconsistent and localized, almost as if controlled. And yet, the total observed acceleration was too small to suggest propulsion. It existed in a gray space between the mechanical and the natural, between the known and the impossible. As news of the anomaly spread, the astronomical community entered a state of controlled astonishment. Papers began circulating in preprint archives. Some teams proposed that 3I Atlas could be composed of exotic ices materials like solid nitrogen or carbon monoxide that sublimate differently under sunlight. Others pointed to photometric irregularities that hinted at an unusually high albedo, suggesting reflective metals or silicate crystals that might form only under extreme stellar conditions. Each theory seemed plausible in isolation, yet none could fully explain the combined data. How could a small, faint interstellar object display both volatile emissions and metallic reflection, while accelerating slightly in a way inconsistent with gravity? The answer, it seemed, lay outside the boundaries of any known classification. In the United States, NASA scientists at the Jet Propulsion Laboratory took a keen interest in the findings. They compared the object's motion to modeled trajectories of known comets and asteroids and found persistent residuals that refused to vanish no matter how the models were adjusted. They simulated outgassing scenarios, collisions, radiation pressure effects, and even hypothetical interactions with magnetic fields. The results were inconclusive. The simplest explanation was that the object was somehow being pushed by sunlight, the pressure of photons themselves exerting force on its surface. But for that to occur at the observed magnitude, 3I Atlas would have to be extremely thin, with a mass-to-area ratio far lower than any known natural rock. It would have to behave almost like a solar sail. That phrase alone reignited memories of the debates around Oumuamua. Could nature produce such an object? A wafer-thin fragment of cosmic debris, light enough to be nudged by starlight? Or was this something manufactured, something engineered? Mainstream scientists hesitated to embrace such speculation, but the thought lingered at the edge of every conversation. Data does not whisper intentions. It merely reveals behavior, and this behavior was undeniably strange. As more data arrived from observatories in the U.S. Southwest, further irregularities surfaced. The light polarization patterns of 3I Atlas, the way it scattered sunlight at different angles, did not conform to standard models of dusty or icy surfaces. Instead, it produced polarization signatures consistent with microstructured materials, perhaps composed of layered or sheet-like forms. This finding caused a quiet ripple among researchers in optical physics, who recognized that such scattering behavior could suggest surfaces unlike those shaped purely by natural erosion or accretion. The scientific tone remained cautious, but beneath the restraint was a growing sense of awe. In one of the more remarkable nights of observation, the Lowell Observatory recorded a transient spectral spike, a brief, sharp emission that lasted less than 10 seconds before vanishing entirely. It could have been an artifact, a cosmic ray strike, or instrumental interference. Yet when cross-checked with simultaneous data from another telescope, the spike appeared again, faint but real. The wavelength corresponded loosely to ionized carbon, a signal often associated with artificial processes or energetic discharges. The observation was never fully explained. It remained a single data point, isolated yet haunting, an unexplained heartbeat from across the stars. The scientists who reviewed these findings were divided. Some urged restraint, reminding the community of the danger of overinterpreting anomalies. Others argued that anomalies are precisely where progress is born. The debates were long and polite, but beneath them lay a shared realization. 3. Atlas was forcing everyone to rethink what normal meant in astrophysics. The neat categories that had once separated comets, asteroids, and debris no longer seemed sufficient. The universe, it appeared, was presenting new kinds of matter, new configurations of motion, and perhaps even new forms of energy interaction. As the object continued its trajectory away from the sun, it began to dim. Yet, paradoxically, its light variations grew more pronounced, as though it were tumbling faster. Data from the Pan-STARRS observatory suggested a rotational acceleration not random, but increasing over time. Something, perhaps the same radiation pressure that altered its course, seemed to be spinning it up. The effect was subtle but measurable, another deviation that refused to fit within the tidy margins of gravitational physics. By then, even the skeptics had to admit that 3I Atlas was unique. It was not behaving like any interstellar object they had seen before. The shocking observation, as it came to be known in headlines and scientific circles alike, was not one single event, but a convergence of evidence, a cascade of small impossibilities that together broke the framework of existing models. A faint acceleration, a reflective surface that defied known materials, intermittent outgassing that made no thermodynamic sense, polarization inconsistent with dust, and a mysterious spectral emission, all pointing toward something that science could describe, but not yet understand. Around conference tables, in late-night virtual meetings across time zones, astronomers debated what these clues meant. Some clung to natural explanations, perhaps a new kind of interstellar fragment, perhaps an ice body shaped by forces we have not yet modeled. Others whispered of possibilities that stretched beyond comfort zones. What if, they wondered, these were not mere wanderers of chance, but messages of design, fragments of something once made for a purpose that time has long erased? 3I Atlas had not only appeared from beyond the stars, it had brought with it a challenge, one that demanded humanity to look again at the heavens and question what it truly knew about the machinery of the universe. When scientists finally turned their attention to the question of what 3I Atlas was made of, they stepped into a fog of uncertainty deeper than any they had faced before. The initial spectral readings offered a tantalizing puzzle: faint light signatures scattered in patterns that seemed to shift depending on the angle and wavelength. Unlike typical asteroids or comets that produce predictable spectral fingerprints, this object's spectrum seemed alive, mutable, and strangely contradictory. Some wavelengths hinted at icy compounds, others suggested metallic reflection, and a few pointed toward something that could not be classified within known chemical or mineral frameworks. For researchers who spent their lives categorizing celestial bodies, 3. Atlas felt like a riddle that refused to settle into a familiar shape. The challenge began with its albedo, the measure of how much sunlight it reflected. Observations indicated that 3I Atlas had an abnormally high albedo for an interstellar object of its size, far more reflective than typical comets or carbon-rich asteroids. Under most models, such reflectivity would suggest a surface covered in fresh ice or crystalline material, but the temperatures it experienced as it passed near the sun should have vaporized such ices long before these measurements were taken. And yet, the reflectivity persisted, implying a surface capable of withstanding intense solar radiation without significant alteration. That paradox alone upended conventional expectations. The simplest explanation, at least initially, was that 3I Atlas was composed of exotic ices: nitrogen, methane, or even carbon monoxide, substances that sublimate under sunlight in ways that could mimic non-gravitational acceleration. Yet, when the detailed infrared spectra arrived from NASA's Infrared Telescope facility, the telltale absorption bands of these compounds were missing. The readings didn't match any known ice compositions. Instead, the data suggested a surface dominated by materials that neither absorbed nor emitted in familiar patterns. Its thermal emission was too weak for its brightness, as though it reflected light efficiently but radiated heat poorly. Such a property hinted at a material not found among natural cosmic bodies, perhaps something thin, metallic, or even layered in structure. Astronomers began comparing 3I Atlas's behavior to laboratory measurements of various exotic materials. Some noticed similarities to thin films of magnesium silicate or complex carbon composites, materials that on Earth are sometimes engineered for high reflectivity and low thermal conductivity. This raised uncomfortable questions. Could nature produce such a configuration spontaneously, or was there something about this object that defied the natural order? Most researchers avoided speculation, but quietly, the data spoke louder than their restraint. The object did not seem to fit into the mineralogical family of any asteroid, nor did it resemble the volatile composition of any comet. It appeared to exist in a space between those categories, something neither rock nor ice, something unfamiliar. Further analysis deepened the confusion. Polarimetric data, which measures how light is scattered by a surface, revealed polarization ratios inconsistent with rough or dusty terrain. Instead, 3I Atlas scattered light as though its surface were unusually smooth or composed of micro-layered sheets. When scientists modeled this behavior, they found that only surfaces with highly ordered structures such as crystalline lattices or metallic grains aligned in patterns could produce the observed effect. No known natural body in the solar system displayed this kind of scattering signature. Even Oumuamua, with its unusual brightness fluctuations, had exhibited more naturalistic patterns of reflection. 3I Atlas, by contrast, seemed engineered for optical precision. In a conference held at Caltech, researchers debated these findings late into the night. Some proposed that the object could be coated in a type of mineral frost, a residue from interstellar travel that had crystallized after millions of years of exposure to cosmic radiation. Others argued that it might be a fragment from the core of a shattered planet, its metallic components fused and polished by the violence of ejection. A few went further, suggesting that prolonged exposure to interstellar radiation could alter surface chemistry in unpredictable ways, creating exotic bonds unknown to terrestrial laboratories. The idea was that cosmic rays might transmute surface elements into complex polymers or reflective silicates, essentially creating a kind of cosmic mirror through radiation aging. It was an elegant idea, but even that failed to explain everything. The density estimates provided another layer of intrigue. Based on its motion and brightness, 3I Atlas appeared to have an extremely low mass-to-area ratio, meaning it was either hollow or composed of very lightweight material. Such an object would be extraordinarily fragile, unlikely to survive ejection from its parent system intact. If it were natural, it would have disintegrated long before reaching the solar system. And yet, it remained whole. The only comparable scenario, some noted, would be if it were composed of something rigid yet ultralight, perhaps a lattice of carbon nanostructures or metallic foams. But no natural process is known to produce such materials in interstellar environments. The universe can form diamonds, silicates, even graphene-like compounds in certain conditions. But none exhibit the macroscopic properties that would account for 3I Atlas's flight stability and unusual reflection. This peculiar mix of high reflectivity, low density, and spectral ambiguity led to one of the most controversial discussions in modern astronomy. Was it possible that 3I Atlas was an artificial object, a fragment of something once constructed rather than formed by geological or cosmic chance? Most scientists dismiss the idea publicly, wary of fueling sensational speculation. Yet privately, the question lingered. If an advanced civilization elsewhere in the galaxy had ever built light sails or thin interstellar probes, fragments of such technology might still drift through space long after their creators were gone. Radiation pressure could propel them between stars, giving rise to trajectories and accelerations exactly like those observed. The resemblance between 3I Atlas's behavior and theoretical models of solar sails was uncanny enough to warrant serious, if cautious, analysis. At Harvard, AVI Loeb and his research group, who had once proposed a similar hypothesis for Oumuamua, revisited their models with new data. They found that if 3I Atlas had a surface thickness on the order of a millimeter or less, sunlight alone could account for its trajectory deviations. That conclusion was not proof of artificiality, but it was consistent with the physical structure more akin to a sheet or plate than a rock. This possibility reignited public fascination, though it divided the scientific community once again. Some argued that invoking artificial origins without direct evidence risked undermining scientific credibility. Others countered that refusing to consider all possibilities was equally unscientific. Meanwhile, data from radio observatories confirmed that 3I Atlas emitted no detectable radio signals, a point often cited to dismiss the notion of technological origin. But even this finding failed to resolve the puzzle. A non-functioning relic, long dead and adrift, would not necessarily emit signals. In fact, silence might be exactly what one would expect from something ancient, a remnant of lost machinery fading into the interstellar dark. For others, the silence simply pointed back toward natural explanations. Perhaps an unusual composite of interstellar dust, perhaps a type of material formed in the violent shock waves of a supernova. The arguments circled endlessly, as they had with Oumuamua, and still the data offered no clarity for scientists in the US and abroad. What made 3I Atlas so mesmerizing was not merely the mystery of its possible origin, but the way it seemed to resist every known category of matter. Its physical behavior, its reflective properties, its resistance to heat, and its apparent structural stability. All of it seemed to whisper that our understanding of material science on cosmic scales might be incomplete. Perhaps there are processes out there in the atmospheres of distant stars, or the depths of galactic collisions that forge matter in forms we have never seen. Perhaps the universe's chemistry is broader, wilder, more creative than the human mind has yet conceived. Every observation brought more complexity. When ultraviolet spectra were captured from orbiting instruments, faint traces of unidentified compounds appeared near the 250 nanometer range, a signature seen nowhere else in the database of known minerals or molecular ices. Some suggested this could be due to radiation-altered organics, complex hydrocarbons shaped by cosmic rays over eons. Others speculated that these features might indicate the presence of silicate metal hybrids, composites where radiation had fused rock and metal into a single crystalline matrix. The idea of such hybridized materials fascinated researchers, suggesting that interstellar space might serve as a crucible where matter transforms in ways unimagined on planetary surfaces. The final composite model of 3I Atlas, constructed after months of observation, depicted it as a lightweight, irregular object with a reflective, possibly layered surface, part metallic, part organic, and part unknown. Its structure seemed to contain voids or hollow segments, as though it were once part of a larger whole. Whether that whole was a natural formation or an engineered construct, no one could say. The data stopped short of revelation, but it pushed the limits of what science could measure and forced researchers to reconsider the very definition of a natural body. In that sense, 3I Atlas became more than an object of study. It became a mirror reflecting the limitations of our understanding. It challenged the assumption that the universe's materials must conform to what we have observed within the narrow bounds of our solar system. It suggested that the cosmos might be filled with matter shaped by forces and conditions we have never replicated in our laboratories. And it hinted that the difference between the natural and the artificial might be far thinner, far more nuanced than our current science allows us to comprehend. When astronomers first plotted the path of 3I Atlas through the solar system, everything seemed to align with expectation. A hyperbolic trajectory, a speed high enough to ensure it wasn't bound by the sun's gravity, and an inbound direction from the outer constellation of Pisces. For a few brief moments, scientists believed they were witnessing another interstellar traveler, much like Oumuamua or Borisov, an object flung from the cradle of another star system, making a brief appearance before vanishing forever into the dark. But as the data began to accumulate, subtle irregularities emerged, whispers of motion that defied the familiar pull of celestial mechanics. Its trajectory did not behave like an inert rock, obeying Newton's laws alone. It twisted slightly, accelerated faintly, and deviated in ways that no model could easily explain. It was as if 3I Atlas were responding to an unseen hand, or to a force not accounted for in conventional gravity. This anomaly was first detected through high-precision astrometric measurements collected by the Pan-STARRS Observatory and cross-verified by the European Space Agency's Gaia mission. The data indicated a tiny but consistent acceleration a few millimeters per second squared directed away from the Sun. Such an acceleration, while minuscule, was unmistakable once the noise was filtered out. For an object of this mass and speed, the only plausible source should have been gravitational interaction, yet the direction of acceleration was the opposite of what gravity would dictate. The first hypothesis proposed was outgassing, the natural release of vapor from sublimating ices, as seen in comets when they heat up near the Sun. But once again, the physics didn't line up. No cometary coma was observed. There were no jets of gas or dust, no visible signs of venting, and no shifts in spectral composition that would indicate volatile release. In every telescope image, 3I Atlas remained eerily pristine, its shape unblurring even as it passed within 1 AU of the Sun. Normally, even faint outgassing events would cause detectable asymmetries in light curves or spectra. Here, there was only silence and motion that defied explanation. Scientists began to model alternative scenarios. Could radiation pressure alone, the faint push of sunlight, be responsible for this behavior? To most astrophysicists, that seemed improbable. For an object hundreds of meters across, the radiation force from the Sun would be negligible. Unless, of course, the object was incredibly thin and light, with an enormous surface area to mass ratio. That possibility reignited memories of the controversy surrounding Oumuamua, which had shown a similar unexplained acceleration years earlier. Harvard's AVI Loeb and others proposed that 3I Atlas, like its predecessor, might be propelled by sunlight in a way that natural bodies rarely are. The mathematics were straightforward but astonishing. If the object had a thickness on the order of a millimeter, sunlight could produce the observed push. The implication was staggering that this interstellar visitor behaved more like a sail than a stone. It drifted with the gentle persistence of photons, bending its path ever so slightly as it journeyed away from the Sun. Astronomers at JPL, eager to find a more conventional answer, explored gravitational perturbations caused by planetary interactions. Could unseen dust, micrometeoroid impacts, or even tiny solar wind effects account for the anomaly? The answer was consistently negative. The acceleration was too smooth, too consistent, to result from random impacts or transient events. The forces of the solar wind were an order of magnitude too weak to matter, and the gravitational influence of nearby planets could not reproduce the observed pattern. It was as though 3I Atlas were gliding along an invisible current, responding not to the Sun's attraction but to the steady pressure of light itself. This realization carried profound implications for orbital mechanics. A hyperbolic path meant the object came from beyond the solar system and would never return. But if radiation pressure was influencing its motion, then its trajectory could reveal information about its physical properties, its shape, reflectivity, and internal structure. By analyzing the minute curvature of its path, scientists deduced that 3I Atlas was astonishingly responsive to light, suggesting an ultralight density that fit perfectly with previous analyses indicating a hollow or thin structure. The more the team studied it, the clearer it became that this was no ordinary traveler. Its trajectory was not simply a matter of speed and direction. It was a signature, an encoded message in motion, telling us something fundamental about its nature. Even more puzzling were the deviations detected after perihelion, the point of closest approach to the Sun. Instead of following the predicted outward arc, 3I Atlas's path shifted slightly off-plane, as though it had subtly adjusted its orientation. The deviation was tiny, less than a fraction of a degree, but statistically significant. Objects do not change planes in space without cause. For a comet, one might blame asymmetric outgassing. For an asteroid, a collision or fragment shedding. But this object did none of those things. Its motion was smooth, coherent, deliberate, even. Some observers likened it to a leaf turning gently on a current of air, rotating as it caught the light differently with each pass. The rotation period data supported this view. Its spin rate slowed slightly as it moved farther from the sun, suggesting torque induced by uneven radiation pressure across its surface. To visualize this, imagine an enormous reflective plate, tumbling slowly through the void. As sunlight hits one side, it imparts a gentle push. As the object rotates, the pressure shifts, causing subtle changes in direction. On Earth, such effects would be imperceptible, but in the frictionless expanse of space, they accumulate, producing measurable deviations over millions of kilometers. This is precisely what the data seemed to show. It was an elegant physical explanation, but it required an object of improbable structure and composition. Nature rarely constructs such sails. As astronomers traced its inbound origin, they discovered that 3I Atlas had entered the solar system on a trajectory, pointing roughly from the direction of the constellation Draco. No known stellar nursery or planetary system in that direction aligned perfectly with the object's motion, meaning its path had likely been perturbed long ago, perhaps by encounters with other stars. Yet its inbound speed and orientation suggested that it had traveled through interstellar space for millions, perhaps hundreds of millions, of years before reaching us. Over that time, cosmic rays, micrometeoroid impacts, and radiation would have eroded any fragile surface. And yet it endured. How could a structure light enough to be moved by sunlight survive such an odyssey intact? This paradox drew comparisons to human-engineered materials like aerogels, carbon composites, or metal foils, substances with high reflectivity and low density. Some researchers speculated that 3I Atlas could be a fragment of an ancient exoplanet's crust, ejected and fused into an ultralight slab by extreme thermal stress. Others imagined it as a natural analog of a solar sail, perhaps formed through processes unknown to planetary science, maybe as a flake from the surface of a supernova-forged world or the debris of a shattered ice giant. But every hypothesis carried a flaw. The survival time, the stability, the near-perfect correspondence between its acceleration and the solar radiation model, all of it pointed towards something finely tuned, not random. As NASA and ESA jointly refined the trajectory model using real-time data, they noticed one more peculiarity. The angle of acceleration shifted subtly over time, consistent with changes in the object's orientation rather than external influence. This implied that 3I Atlas was tumbling irregularly, not in the chaotic manner of a broken rock, but with quasi-stable oscillations. In effect, it was precessing, like a gyroscope slowly tracing circles in space. Such behavior could result from its asymmetric shape, but the pattern seemed strangely balanced, as if its mass distribution had been engineered to maintain a slow, controlled rotation. This led some dynamicists to compare it to spacecraft debris or sail fragments, objects known to behave similarly when drifting beyond Earth orbit. Still, the data remained ambiguous. Every possibility, natural or artificial, required assumptions that stretched the boundaries of plausibility. What scientists could say with certainty, however, was that 3I Atlas's motion did not fully obey gravity alone. There was another hand at play: radiation, structure, or something yet unknown. Its defiance of simple physics echoed through scientific journals, reigniting questions not just about what it was, but about how much we truly understood about the subtle forces that shape motion in space. The U.S. astronomical community responded with renewed vigor. Proposals flooded into NASA and NSF requesting telescope time to observe similar faint, fast-moving interstellar objects in the future. The Space Surveillance Network, originally designed to track satellites, began integrating algorithms to detect non-gravitational accelerations in deep space trajectories. The logic was clear. If 3I Atlas was not unique, then others like it might already be crossing the solar system unnoticed, their faint signatures lost in data noise. Detecting them could open an entirely new field of astrophysics, bridging the gap between celestial mechanics and materials science. The notion that sunlight itself could sculpt an object's motion so precisely, turning photons into navigational force, captured the imagination of both scientists and the public. It evoked visions of humanity's own future solar sails gliding between stars, powered only by the energy of light. And in that poetic symmetry, 3i Atlas became both a mystery and a metaphor. Whether it was a relic of alien craftsmanship or a quirk of nature's infinite inventiveness, its trajectory told a story about the cosmos' hidden elegance, a story written not in words, but in motion, tracing a line across the solar sky that bent, however, slightly, against the pull of gravity. As the data on 3i Atlas poured in from telescopes around the world, the excitement that initially united the scientific community soon fractured into one of the most heated debates in modern astronomy. It was not simply about what 3i Atlas was made of or how it moved, but what it meant. At the heart of the controversy lay an uncomfortable truth. The object defied every established framework of understanding. Each new dataset seemed to challenge the boundaries of known physics, and as a result, scientists found themselves divided between cautious empiricism and bold speculation. What had begun as a straightforward observation had evolved into a philosophical confrontation about the nature of science itself, about how far one could stretch conventional reasoning before acknowledging the possibility of the extraordinary. In the United States, where many of the world's leading observatories and research institutions are located, the debate became especially intense. NASA's Jet Propulsion Laboratory, Harvard University, and the University of Hawaii, all instrumental in tracking 3i Atlas, released preliminary papers that seemed to contradict one another. Some argued that the object's non-gravitational acceleration could be explained by natural processes, such as volatile outgassing or rotational instability. Others pointed out that no such signs had been observed, and the precision of its motion suggested a more exotic explanation. Within academic circles, the mere mention of artificial origin stirred controversy, triggering echoes of the same debates that had once surrounded Loeb, the Harvard astrophysicist who had famously suggested that Oumuamua might be a piece of alien technology. Re-entered the conversation with renewed conviction. He argued that 3i Atlas reinforced the case for considering artificial explanations when natural ones failed to satisfy the evidence. His paper, circulated widely online, proposed that 3i Atlas could be a fragment of an interstellar lightsail, a technology designed to harness radiation pressure for propulsion. Loeb emphasized that such a hypothesis was not science fiction, but a plausible interpretation consistent with observable data. However, many of his peers accused him of sensationalism, suggesting that such claims risked turning astrophysics into tabloid fodder. Astronomers from the European Southern Observatory, the California Institute of Technology, and other leading research centers took a more conservative stance. They argued that unknown natural mechanisms could easily explain the anomalies. Perhaps, they proposed, the surface of 3i Atlas was composed of materials that interacted with sunlight in unusual ways. Or maybe the object was fragmenting on a microscopic scale, releasing particles that created subtle accelerations too faint to be detected directly. Others speculated that the deviation in its trajectory might not even be physical, perhaps an artifact of measurement error, or the product of incomplete models of solar radiation dynamics. To them, invoking extraterrestrial engineering without irrefutable proof was premature, even irresponsible. For the American audience, the story of 3i Atlas carried echoes of the nation's earliest explorers, pioneers who crossed oceans and continents in search of understanding. The spirit of discovery, embedded deeply in the American consciousness, found new expression in the stars. Scientific institutions across the country emphasize this connection, using 3i Atlas as a teaching tool to inspire students in physics, engineering, and astronomy. Outreach programs flourished, planetariums filled with visitors, and young people once again began dreaming of careers in space science. The mystery had reignited the emotional core of exploration, the belief that looking upward is synonymous with progress. This new era of cosmic observation also forced a reckoning with the philosophical meaning of knowledge itself. For centuries, science has sought to reduce the unknown into patterns and equations, transforming mystery into comprehension. Yet 3i Atlas demonstrated that some mysteries resist reduction not because they are unknowable, but because they require a broader kind of understanding, one that embraces complexity and uncertainty as part of the truth. This realization marked a cultural shift. Science, rather than being a process of domination over nature, became a dialogue with it. Humanity, through observation and humility, was learning to listen. In that sense, 3i Atlas was not just an astronomical event, but a mirror. It reflected the state of human curiosity, our capacity to question, to wonder, to imagine beyond ourselves. It showed that even when faced with the incomprehensible, the human response is not retreat, but exploration. The silence of the object was not emptiness, but invitation, a challenge to continue looking outward with patience and courage. It represented the perfect union of science and philosophy, reason and reverence, reminding us that knowledge and awe can coexist in the same breath. As telescopes turned away and the data faded into archives, the impact of 3i Atlas continued to ripple across disciplines and generations. It became a symbol of humility in science, a case study in open-minded investigation, and a reminder that the universe is not merely a collection of distant lights, but a living system of interconnection and evolution. The object's mysterious journey past our planet expanded not only our understanding of interstellar phenomena, but also our awareness of the fragile, fleeting moment we occupy in cosmic history. In the glow of its passing, a new awareness settled into the human consciousness, that the universe is not static, not silent, not indifferent. It is a vast ocean of possibilities, and every so often, something like 3i Atlas drifts by to remind us that even in the immensity of space, there are stories waiting to be discovered, questions waiting to be asked, and perspectives waiting to be transformed. As the mystery of 3i Atlas fades into the distant dark of interstellar space, what remains is not merely data or speculation, but a profound awakening of human curiosity. This singular object, traveling silently through the solar system, became a symbol of our species' greatest strength, the relentless drive to understand the unknown. It reminded scientists, dreamers, and skeptics alike that the cosmos is not a closed book, but a living story still being written in the language of light, gravity, and imagination. Every calculation, every observation, every theory born from this discovery was a reflection of the same timeless question that has guided humanity for millennia: what lies beyond? 3i Atlas forced us to confront the fragility of our knowledge and the limits of our instruments. It humbled the scientific community, revealing that even with our most advanced telescopes and computers, there are phenomena that still defy comprehension. Yet within that humility lies the essence of progress. The courage to question, to doubt, and to look deeper. From the early days of observation to the philosophical debates it inspired, 3i Atlas became more than an astronomical object. It became a mirror, reflecting both the brilliance and the vulnerability of human understanding. For astrophysicists, it redefined the boundaries of celestial mechanics and interstellar dynamics. For astrobiologists, it opened a new frontier of inquiry, where life, intelligence, and cosmic artifacts could no longer be dismissed as mere fiction. For philosophers and the public, it reignited the wonder that first drew humanity to the stars. The quiet recognition that our place in the universe is both infinitesimal and extraordinary. Each possibility that 3i Atlas presented, whether as a natural traveler, a messenger from another system, or even an artifact of distant intelligence, carried within it the same truth: the universe is far richer and stranger than we have dared to imagine. As we stand beneath the same stars that watch 3i Atlas pass, we are left with a renewed sense of wonder. Somewhere in the vastness of space, countless other objects like it may be drifting, remnants of creation, fragments of civilizations, or simply travelers of the cosmic sea. The story of 3i Atlas is, in truth, the story of us, of our curiosity, our ambition, and our willingness to chase meaning across the void. It connects the ancient stargazers who charted the heavens with the modern scientists who decode its secrets, forming a continuous thread of awe that defines the human experience. And though 3I Atlas has vanished beyond the reach of our telescopes, its legacy endures. It has changed the questions we ask, the tools we build, and the way we see ourselves in the universe. It stands as a quiet reminder that the cosmos is not finished revealing its surprises, that the next discovery may be even more astonishing, and that the pursuit of knowledge is itself a journey without end. In the wake of its passing, humanity looks once again toward the stars, not for certainty, but for connection, for meaning, and for the unending promise that somewhere out there, the universe is still whispering secrets to those who dare to listen.